Good evening, welcome to video 6 of topic 1 of unit 3, calorimetry. This video we're going to be covering calorimetry and examining some different types of data related to it that you may see on exams and other type of sources there. So here are your learning intentions and success criteria. Please pause the video and complete the KS table down here on the right. Okay, so having a look here, we can see we're looking at some new types of verbs. There's that familiar calculate verb, but there's another one there, construct calorimetry equations, and we want to be able to apply this knowledge that we've learnt about specific heat capacity and phase changes to solve some of these problems. So the one thing we do need to know is, well, what is calorimetry in the first place? If we don't know what that is, we're not going to really be able to use it. And secondly, well, can we construct and do these calculations? So we're just jumping straight into the worked examples here. Calorimetry is just the study of heat transfer within substances, normally to work something out. We saw a little bit of it with our previous worked examples, where in the last two videos we looked at single substances with and without phase changes. Now we're going to look at examples of mixtures, whether that's mixing two liquids or a solid and liquid, or having two solids in contact with each other, as well as looking at, I shouldn't say liquids, I should say fluids, because the same things for liquids as they would for gases. And then we're going to look at how this data could be represented on an exam or in graph type format in your student experiment. So we can jump straight to the worked examples. This first one here is the worked example from 2.3a, which is one that I did not do in any of the previous videos, because this one here is now looking at all these mixtures and what happens when we combine things together. So it reads, a 70 gram copper block at a temperature of 80 degrees Celsius is placed in contact with another copper block at the same mass at a temperature of 20 degrees. Calculate the final temperature when the blocks have reached thermal equilibrium. Now, the first big idea we have to assume here is that the energy that one block loses only goes to the other block. We're not worrying about the air around it, or how cold the room is there a breeze. We're just pretending that the system is perfect and it's only one block losing it to another block. The core idea of all these equations, or all these questions that we're going to use, is that the change in energy, Q, remember our Q equals MCAT formula, of one substance plus the change in energy of another substance equals 0. Okay, this is the first law of thermodynamics, that the energy change from one thing must equal the energy change from another thing. Or if we think back to year 8, it's the law of conservation of energy, and we talked about that in a previous video. So using this principle, this is going to govern all our equations and math we do from here. Q might be very simple, it might just be one Qmat. Q could be quite complex, and using a Qmat for one phase, then a phase change, and then a Qmat for another phase. It doesn't matter what is going on. If it's very complicated, we just need to put each of the steps in. It's still going to be the same basic idea. Now, the textbook, if you have a look at the worked examples, don't lead with this. They lead with something that looks a bit more like this. QA equals negative QB. Okay? And so this is how you can certainly feel free to start your math if you wish to, but if you kind of get stuck on, how do I do this, where's the negative go, and it doesn't matter which side the negative's on really, start with this. The change in energy of one thing and the change of energy of another thing must equal 0. A closed system must sum to 0. This is the first law of thermodynamics. So let's have a look at this. Our QA, that's copper block 1, and our QB, that's our copper block 2, the cold one. So let's start looking at this. Well, we've got two things. It's reasonable to assume that if one thing's at 80 degrees in solid and one thing's at 20 degrees in solid, there's not going to be any phase changes, so we just have a Qmat going on. So I'm going to use Qmat, or MC delta T of A, and what I'm going to, that's a weird looking A. What I'm going to do, I'm going to put all of that A outside the brackets, equals negative MC delta T of B, and again all of that outside the brackets. You could write, and if you have a look at the textbook, that's what they do. They've got M hot copper, C copper, TFTI, M cold copper, C copper, TFTI. I'm lazy. I'm just going to put it in there once. You're perfectly okay to do it. So let's see, the masses on both sides are 70 grams. So let's write that as a thing. We have 0.07. And over here, I'll just expand this out, 0.07. Oh, I can't forget my negative there out the front. C of copper is equal to 390. Now remember, on an exam, if we expected to use it, it'll be provided. If you need to work it out, you'll need to work it out. However, if you're doing questions for your exam practice or for your practice and questions, remember you need to look probably in chapter 2.2 for some of these QMATs, and from these latent heat capacities, specific heat capacities, and in chapter 2.4 for your latent heat capacities. So as I said, this is equal to 390 times, now delta T, remember, is final take initial. We don't know the final, so I'm just going to put TF for final. Okay, but we do know the initial. So one of these copper cubes starts at 20 degrees, one starts at 80 degrees. Okay, I'll just put the rest of the stuff over here, times 390, and it ends at TF, which we don't know. It's up to you what you put on what side. Okay? And actually, it doesn't even matter. Okay, because if I have the negative here, and the negative actually should be over there because this is the one that's getting colder, it'll still work out. So one of them has to be the one substance, one is the other substance. I always like to go, well, this one's getting colder, so I put the negative out the front, and that means my 80 degrees is going to cool down and meet the 20 degree one somewhere. Okay. Now, if we have a look on this, this is a nice easy one. We can see that this side has a 0.07, this side has a 0.07. They're going to cancel. This side has a 390, this side has a 390. They're going to cancel. And now we're just left with TF minus 20 equals negative TF minus 80. TF minus 20 equals negative, don't forget the bracket, TF minus 80. We propagate that in, that will become TF minus 20 equals negative TF plus 80. Let's simplify this. So I'm going to take the negative 20 to the other side, and we're going to add that over there. We're going to add this to this side, so we're going to have 2 TF equals 100, and so TF equals 50 degrees Celsius. Now if we think about it, if I have two substances, one's at 20, one's at 80, it makes sense the middle point would be 50. Now, I would recommend you do this worked example for yourself. If you forget that negative sign, you're going to get an answer probably around 30 degrees according to the text. While that's not a completely unreasonable answer, because normally when these things go wrong, you end up with like a negative number, or you end up with a number that is lower than either of the starting points, which doesn't make sense. If I have something at 10 degrees and something at 100 degrees, if I mix them together, they should be somewhere between the two. One's not going to suddenly get colder, and the other, is going to reach the same colder temperature. But 30 degrees again, oh, that's somewhere in between, so maybe that could work. In this case, the fact that the masses and the materials are the same should clue you in that no, it can't work, because it needs to be halfway between the two. Okay, but this method is what we're going to do all the time. So let's have a look at worked example B. Oh, I did have my specific heat capacity for copper. Here's worked example B from chapter 2.3. 50 ml of hot water. Remember, 1 ml weighs 1 gram. Hot water at 80 degrees is mixed with 150 ml of cold water at 5 degrees. Calculate the final temperature. So now we have different masses. We still have water, so we still have the same C value, but we have different masses. Let's have a looky here. So I'm just going to jump straight to this version of the formula. Negative, oops, I didn't turn it over onto ink, so let's do that. Pen, negative, okay, Q of, let's go 1 equals Q of 2. We could use A, we could use B, we could use, the text is using L and G for loss and gain. That's not a bad thing, right? But I don't really care too much what you do. When you've got different materials, it's a lot easier. If you're doing stuff like copper and water, well, great, C for copper and W for water, that's nice and easy. But in this case, it can be a bit tricky. So let's expand this. MC delta T, and that's all number 1, equals MC delta T number 2. Let's start putting our values in. Our mass is equal to 0.05, oops, don't forget my negative sitting out at the front, times our specific heat capacity of water, 4180, times our change in temperature. So TF, we don't know what TF because we don't know what it's mixing to. We do know that it starts at 80 degrees, and that's the one that starts hot and is going to get cold, so I'm going to put it with my the negative one, the one that's going to lose some energy, equals, in this case the mass is different, so 0.15 times 4180 times our temperature change, TF, we don't know what that is, take away, and we see it starts at 5 degrees. Alright, now, having a look through this, we can see there's a 480 on both sides, just cancel those off, and now you've only got to deal with our one number and our TF change. Now, first step is the text does it a little bit differently. They don't cancel off the 4180, so I'm going to work this one through for us. We're going to have 0.05 or negative 0.05 times TF plus, that's the tricky bit, this is the thing a lot of people get caught on. There's a negative here times a negative, we're going to have a plus. And so we have 0.05 times 80, which will give us 4, equals, now we have 0.15 TF, okay, and then we have 0.15 times negative 5, so it will be a negative. 0.15 times 5 is going to be negative 0.75. Now we can simplify all our stuff together. I'm going to add this to the other side, and I'm going to add this to the other side, so I'm going to have 4.75 equals 0.2 TF. TF equals 4.75 over 0.2, and that will equal, should equal 50 degrees. So 4.75 divided by 0.2. I've done a mistake here somewhere. Oh, sorry, I was looking at the wrong worked example, just to double check. Textbook has 23.8, which rounds off as 2 significant figures, because if we have a look through here, we see they had 50 mil, that's 2 sig figs, so that would be 24 degrees Celsius. Okay. Now if we think about it, we had not much water at 80 degrees, but we had 3 times the amount of water at 5 degrees. So the reason it didn't meet in the middle is because there was a lot more cold water than there was hot water. Okay? I always like to think, is this a reasonable answer? It'll help you double check your things. Okay, next example. We've got a few examples on this one. Here now we've got 2 different materials. We have the 100 grams of alcohol, ethanol, is the specific alcohol in this case, mixed with 250 grams of water at 20 degrees. What's the final temperature of the mixture? Now, I have put our specific heat capacities here. We're going to do the same thing. Let's see, the alcohol is at 50 and the water is at 20 degrees. So I predict, fairly rightly, that the ethanol is going to lose the energy and the water is going to gain the energy. Okay? And if you have a look at the worked example for 2.3c, you can see that's what Wilding's done there. He's gone minus QL. I'm assuming he's using L for loss, as I said before, but then he's put alcohol after it because that is the thing that is losing energy here. Let's write our formula out. Negative MC delta T, I'll put E for ethanol, equals MC delta T for water. Just to show you what I mean by propagating that out, some people will go MWCW delta T W, and sometimes they'll even expand the delta T and do TF, take TFW, take TIW. I just find that's too much work to do. It means the same thing as long as you're not confused by it. If you'd rather do that, feel free, but I'm just trying to save you guys a bit of hassle down the track. So having looked through our formula, we have our mass. We're told it's 100 grams, so that's going to be negative of 0.1. The specific heat capacity of alcohol is told as 2450. Now, sometimes when you are doing these sort of calculations and you go, I don't have the one that says exactly ethanol, because there are some other types of alcohol. Methanol is another really common one. You might have it at home, commonly called methylated spirits. If you're uncertain, just take best guess at what you think the C might be, and then if the answer comes out wrong, try to work backwards, or if you are uncertain, email me and we'll see what we can work out. But practicing the skill, don't let perfect get in the way of being good and practicing the skill. And we have our change in temperature. So the ethanol, we say, starts at 50. So TF we don't know, but it starts at 50. Now the mass of the water, 0.25 grams of water times 4180 times TF take, we say it starts at 20. Oops, didn't need that extra bracket there. Okay, and now we just work our way through it. So 0.1 times 2450 is 245. So we're going to have negative 245 TF. Negative times a negative is a positive, plus 12250. 12250. You can feel free to do this bit in the middle times TF, this bit times the negative 50, and then on the next line after multiply by the negative. But I mean, the math isn't too hard. You can figure out what's best for you in terms of how much working you need to do. 0.25 times 4180 is going to be 1045, and multiply that by a TF. 1045 TF minus, and that's going to be 20,900. Let's rearrange our stuff so we can, if we add that to that side and add that to that side, everything will be positive. If you look at the worked example, Walding makes everything a negative. It still gets the same answer because both sides will be negative. I just kind of like positives. So we add that over to that side. We're going to get 1295 TF is going to be equal to 33150. 33150. So TF will equal 25.6 or 26 degrees Celsius at 2 sig figs. If we have a look at here, we can see it's the water started at 20. It did go up a little bit. There's a lot more water, so that makes sense. And if we look at the specific heat capacities, we can see water takes like nearly twice as much as alcohol. So if we had, this would be very similar if we had 500 grams of alcohol mixing with 100 grams of alcohol with these temperatures. We'd end up with a pretty similar number there. Because water's got such a high specific heat capacity, it takes a lot to get it up, even just a small amount. So those ones are all our liquidy ones. Now we're going to have a look at some solidy ones. Here we have, let me read it off, 20 gram stainless steel spoon at room temperature, 20 degrees Celsius, is placed in 200 mils of coffee at 70 degrees in a foam cup. Assume the foam cup doesn't absorb any energy. That's the, basically that's the author, they're going, let's make this easy and only deal with two things. If the foam cup did absorb it, we could still model it without much of an issue. You just have QMAT with three objects. The bit that's losing energy would be just the coffee, but the bit that's gaining energy would be both the spoon and the cup. The math is not any harder because you still only got one variable of TF. You just have a new mass and a new specific heat capacity. If you are going to do specific heat capacity type things for your student experiment, and certainly a good thing to do because it's not a terribly hard thing and we have the technology for it, like you can use an infrared thermometer to measure the temperature of the cup on the outside. You could do this as a way of going, well, trying to account for energy losses in your modelling. So that could be something. A 3-variable thing would be quite complex, especially for a senior student, but it could help you demonstrate thoroughness and understanding the theory. So we have something getting cold, we have something getting hot, we do exactly the same thing. The fact that one's a liquid doesn't mean bunk to us. We're just going to do, well, what's losing energy? The coffee's losing energy. Minus, oops, I need to, what did I do there? Apologies. We're going to assume that the coffee's just water. Okay, and I don't have my specific heat capacity of steel here. Whoops, I should have got that. So you'll have to head back to chapter 2.2, I think, to get that. We're going to have our minus Q of coffee equals, the positive Q of the steel spoon. Write the same formula. MC delta T, and I'm going to put a little C, equals MC delta T, all of our S. The mass of the coffee, as the question says, it's 200 mils. We're going to assume it's basically the same as water. It's not, obviously, but being as I don't have a specific heat capacity, for any particular type of coffee mentioned here in the textbook, coffee is mostly water. Let's just use that. Okay? So our mass is equal to, well, it's 200 mils, which is the same as 200 grams, 0.2 times 4180, don't forget my negative, times temperature final, we don't know, and the initial temperature says 70 degrees, equals, mass of the spoon is 20 grams, 0.02, specific heat capacity of steel is equal to 500, again it is in that table back at previous chapter, TF, take away, and the spoon starts at 20 degrees. We don't have the same materials, we can't cancel stuff off, so we're just going to work our way through it. So this would equal, if we propagate that through, negative 836 TF plus negative times a negative 520, and over on this side we're going to have 10 TF. Negative times positive is a negative, and take away 200. Okay, now that we have those, let's rearrange. So we could subtract that to that side or add that to that side. It doesn't matter what you prefer to do. However, I certainly prefer to make things positive. It does look like the text makes a bit of an error here, and they've got 850 TF. So I'm going to double check Mr. Walling's math for a second. 0.2 times 4180. Okay, so it looks like this number is definitely correct, but the next number here should be negative 846 TF equals negative 58720. That looks like a correct number on that side. The negatives don't matter, as I said, because negative on both sides cancels. 58720 divided by 846 gives us an answer of 69.4 degrees. TF equals 69.4 degrees. But if we go back to our question, the most accurate thing we have is 2 sig figs, so this would round off at 69 degrees Celsius. Nice. Alrighty, now that's why sometimes you got to double check these things, and you might notice a math error. In fact, I'll probably go have a look at the errata just to make sure this is being picked up, but I assume someone would have picked this up last year. So those are our our 4 worked examples there, and you can see it didn't matter if we're mixing fluids with fluids, or solids with fluids, or solids with solids. It was the same process every time. Okay? The math looks scary, but it's just working through the steps by steps. The hard bit is just constructing that first equation. Once you're through that, it's substitute the values, work the problem with algebra. It's not really much different from algebra you did in year 7. It just looks scarier because there's more things in it. So now we're going to look at some graph style data, and we're going to use this general approach. You can always use this approach for any question with the graphs and your student experiment. So that's why I kind of like this. So first thing you have to do, 1, identify what your gradient is. Include your units. This is really similar to that prac we did with water and oil, where we had to use the gradient to work out the power and then use the gradient to work out the specific heat capacity of oil by using data from our experiment. Don't forget to work out the error in the gradient. Choose an equation that you can work the gradient into, and you might have to manipulate it. Like we saw with our power equation, our Q equals MCAT and our power equation. We had to combine the two, so then our temperature over time could be worked into it. Apologies, just had to clean off some sweat. It's very hot tonight. And then finally, you do your solution and you do your error calculations. So let's have a look at a couple of practical examples. This is an example from an exam used at another high school. I forget which one I've actually got this out of. But we can see here we have a nice 3-line graph. We can see, well, here's the temperature of something, and here's how much energy has been changing in the system. And we've got this lovely pretty graph here, and realistically, outside of looking at the units, and we can see here the units are going to be joules divided by degrees Celsius. Outside of that, the graph really doesn't mean anything to me. This is what I want. Like we practiced in class, here's my equation and my trend line. So here's my maximum and here's my minimum. So remember, my error will equal max take min over 2. So for my gradient, I'm going to use symbol Z, will be 369 take 324 over 2. What's that going to equal? 69 take 24 is equal to 49, is equal to 45. 45 over 2, which should be 22.5. So there's the error in my gradient, and my intercept is going to be, now there are negatives there. You should use them because negative 7750 take away negative 6250 is pretty similar to 7750 plus 6250. It should be very close to the same, but it will be a positive versus a negative. However, what you should keep in mind is that when you plus minus, the sign doesn't really matter. So I always keep the negative there when I'm doing the working, that way I don't have to second guess anything. Take away negative 6250 over 2. So let's see, negative 750 plus 6250 divided by 2 is equal to 750. I'm just going to remove that, so that's picking up my hand. So the error in my C value is equal to negative 750. We don't really need that negative, so I'm just going to cross it out, because adding and subtracting a negative is the same thing as adding and subtracting a positive. Okay, so we've got our gradient, so there's our errors, and our gradient equals 341. Okay, and there's our units, joules per degree Celsius. So let's have a look at some formulas that we have involving energy and temperature. Okay, and notice it says temperature changes, so that delta T. The first one that really stands out is Q equals MC delta T. Alright, we've been working with this formula, it should pop out. Remember, there's only like 5 formulas when it comes to heat capacity, so if you've got things that are heating up, it's probably going to be this thing. Let's see if we can rearrange this so that we have these units. I'm going to show you a trick here. I'm going to rewrite this using the units. Q is measured in joules. Mass is measured in kilograms. Specific heat capacity is measured in joules per kilogram degrees Celsius, or Kelvin is the normal way of saying it, but because we've got a formula in degrees Celsius. And you might be going here, ooh, there's a joules per degree Celsius, so maybe this is equal to C. But don't forget, if I was to finish this off, I also have a degrees Celsius here. And if I divide this delta T to the other side, if I do Q over delta T equals MC, well, now I have my gradient of Q over delta T is my joules per degree Celsius equals the mass times the specific heat capacity. So if I had a formula, if I had a graph like this, I could take that gradient, and we can see here my gradient is equal to joules per degree Celsius, but joules per degree Celsius is also equal to mass times specific heat capacity. Okay, if I wanted to get that joules over degrees Celsius here, I'd have to multiply these two things together to get rid of the kilograms. So that means if I know the mass of whatever I'm heating up here, I could work out this, the specific heat capacity. If instead I knew the specific heat capacity of whatever substance I'm using, I could work out the mass of it. Now, being as that's 341, that would be something like perhaps a small amount of brass. Okay, brass has a specific heat capacity of 380. We're going to be working with it, so it could be like a 80 to 90. An 800 to a 900 gram block of brass there, because it's just a little bit under the 1 kilogram mark. But that's all we need to do. Now, we would then have to do some of this math with it, because I'd need to have my mass value, and there'd be an error in my mass value, and I've got my error in my Z value there. And you might go, well, what about this error in my C value? Well, we didn't use it for anything. There's no plus C on this expression unless you expand it. The plus C would then become part of the initial temperature, but that's way more advanced stuff down the track. The other type of graph you might see, I do give myself some space to get rid of some of this. Excuse me. This is the other type of graph. We have here two different experiments, both graphed on the same thing. We can see up on our key, we have gold, we have iron. Here's the water with the gold in it, and here's water with the iron in it. This would be very similar if we could track the individual temperatures of the different materials that we use in our experiment. And Year 12s, this might help you a little bit with thinking about what you did last year in chemistry, if you took chemistry, where we have gold and water here starting at nearly 100 degrees because it's been placed in boiling water. Both of them are cooling down, and we can see that the water plus gold mixture, after we drop it in, the water is starting to heat up slowly. So we can see the water and iron rises till it meets the iron mark, and the water and gold rises till it meets the gold mark. One thing I can infer from this is because the iron goes to a higher value, it must have more energy stored in it than the gold, so it must have a higher specific heat capacity, assuming the mass is the same. If this experiment was using different masses, we wouldn't be able to really guess too easily off this. But we have here an initial temperature, a final temperature. If we know the masses of these substances, and perhaps there's, for example, 100 mils of water and a 10 gram cube of iron, we could then work out the specific heat capacity of iron. So this would, again, instead of using formulas and working out gradients, is more going to be around the idea of, well, I have my formula, MC delta T, let's make this one negative, equals MC delta T. This one could be gold, and this one might be water, or the water plus gold. We have our initial and final temperatures. The masses would be the things we set up in the experiment or told to us on a question, and then the C's would be things we could figure out from our experimental data. What I need you to sort of clue into here is that it really just comes down to what formula can be applied to this question. Whether your question is written in words, like the worked examples from the textbook, or the data for your question comes from a graph, it's still the same thing. It's just how they're presenting to, so it really becomes a literacy issue where you just need to read different types of information. Now, this has been a pretty heavy video. I do appreciate that. I left a blank slide there. For your lesson summary, we have done the following thing. We've applied our knowledge of calorimetry to experimental data sets, and we've constructed and calculated these equations. For your entrance slip, please have a look at chapter 2.3, questions 1 to 6, and copy them into the answer space on 3.1.6. I will just have a quick look at them. A couple of them are written, but questions 4 through to 6 are calculation type things, and so you'll be able to get your answer pretty quickly there. Okay, great. Really hard lesson, I do understand that. Good work though. Night guys.